January 17, 1917, Pittsburgh, Pennsylvania, the Alcoa Research Laboratory. The winter cold seeped through the brick walls of the narrow laboratory on the northern edge of the city, where the Allegheny River bent like a question mark toward the industrial heart of America. Inside, beneath flickering Edison bulbs that cast long shadows across workbenches cluttered with metal samples and crucibles, a young metallurgist named Alfred Wilm's notes lay spread before a team of American engineers who had never met him. The pages, smuggled from Germany through neutral Switzerland, described an alloy the Kaiser's war machine had discovered by accident. Duralumin, they called it, a marriage of aluminum and copper that grew stronger as it aged, as if time itself were a forge. Outside, newsboys shouted headlines about German U-boats sinking American merchant vessels in the Atlantic. The United States teetered on the edge of war, and the men in that cold room understood what Washington did not yet fully grasp. The next war would not be won in trenches alone, but in the sky. And America, for all its industrial might, possessed not a single pound of aluminum suitable for flight. The irony would have been almost poetic if it were not so catastrophic. The United States, which had given birth to powered flight barely 14 years earlier on a wind-swept beach in North Carolina, could not build the very machines the Wright brothers had pioneered. Every military aircraft in the American arsenal, all 35 of them, a fleet so small it could fit on a single airfield, relied on wood and fabric, ash and spruce stretched over frames that groaned in high winds. The aluminum used in what few metal fittings existed came from European suppliers, shipped across an ocean now prowled by submarines. Britain's Royal Flying Corps soared over the Western Front in machines skinned with aluminum alloys. Germany's Fokkers and Albatrosses dominated the skies with metal structures that could withstand punishment wooden frames could not. France, Italy, even Russia, nations America would soon call upon for help, had mastered the metallurgy of flight. The country that invented the airplane could not build one that would survive modern combat. This was not supposed to happen. Aluminum itself was an American triumph, or it had been made so. In 1888, a young chemist named Charles Martin Hall had perfected the electrolytic process that transformed aluminum from a rare metal more precious than silver into an industrial commodity. By 1900, the Pittsburgh Reduction Company, soon renamed the Aluminum Company of America, Alcoa, had driven the price from $18 per pound to just 33 cents. Aluminium flowed from Alcoa's smelters in vast quantities, enough to wire cities, build cookware, wrap chocolate bars. But making aluminium cheap and making it strong were entirely different problems. Pure aluminum was soft, almost butter-like in its malleability. It bent under pressure. It fatigued under stress. It was, in every engineering sense, unsuitable for the brutal demands of aviation, where metal must withstand not only gravity but vibration, temperature swings from desert heat to Arctic cold at altitude, and the violent forces of combat. Bullets tearing through wings, shrapnel punching through fuselages, the wrenching torque of engines pushing propellers faster than sound itself at the blade tips. The German alloy Wilm had discovered changed everything, or it should have. In 1906, working in a laboratory outside Berlin, Wilm had been attempting to harden aluminium when he noticed something extraordinary. A sample of aluminum alloyed with small amounts of copper, magnesium, and manganese grew significantly harder after several days at room temperature. The metal aged like wine, its crystal structure rearranging itself into a stronger configuration through a process he did not fully understand, but could reliably reproduce. Duralumin, he called it, from the Latin durus, hard. The German military recognized its potential immediately. By 1914, Count Ferdinand von Zeppelin's rigid airships, those vast, hydrogen-filled monsters that could cross the English Channel to rain bombs on London, flew with duralumin frames. The Kaiser's aircraft industry, though still largely wedded to wood, had begun experimenting with all-metal aircraft designs that promised to revolutionize aerial combat. But Wilm had patented his discovery in Germany, and his employer, Duraner Metallwerke, guarded the secret jealously. When war erupted in August 1914, that secret became a strategic asset, protected by naval blockade and diplomatic silence. The exact composition of duralumin, the precise ratios of copper to magnesium, the heat treatment temperatures, the aging schedules, remained locked behind the walls of German industry. Allied metallurgists knew duralumin existed. British intelligence had recovered fragments from crashed Zeppelins over England, enough to confirm its basic composition, but not the subtle details that made the alloy work. The French duplicated some results, but America, which entered the war in April 1917 with the smallest air force of any major power, had nothing. Zero. Not a single domestic alloy that could be formed into aircraft-grade sheet metal and reliably machined into the 1,000 components a military airplane required. This was the crisis that brought those men to the Alcoa Laboratory on that January morning. The company had been experimenting with aluminium alloys for years, driven partly by scientific curiosity and partly by commercial necessity. Alcoa enjoyed a near monopoly on American aluminium production, and monopolies survive by creating new markets for their products. But aviation had been a niche concern, a hobby for daredevils and exhibitionists. Now, suddenly, it was everything. If America could not build aircraft, it could not protect its soldiers, could not scout enemy positions, could not challenge German air superiority over France. The War Department had begun to grasp the magnitude of the problem. Aviation officers submitted urgent requests for modern fighter planes, bombers, reconnaissance aircraft, machines that existed only in British and French factories an ocean away. President Woodrow Wilson, who had campaigned for re-election on keeping America out of war, now faced the prospect of sending an army to Europe that would fight half-blind, vulnerable to attack from an element his forces could not contest. Alcoa's researchers approached the problem with the methodical intensity American industry had perfected during the previous century's industrial revolution. They began by acquiring every scrap of information available about German duralumin, every intelligence report, every captured fragment analyzed by British metallurgists, every rumor and educated guess. They studied Wilm's published papers from before the war, parsing his careful German prose for clues about composition and process. They built upon earlier Alcoa experiments with copper-aluminium alloys, some dating back to the turn of the century, dead-end research that suddenly acquired new relevance. And they tested. Endless, systematic testing. Mix ratios varied by fractions of a percent, heat treatments calibrated to the degree, aging schedules measured in hours, then days, then weeks. Each sample cut into strips and subjected to tensile tests, bending tests, fatigue tests that simulated the vibration of an aircraft engine running at full throttle for hours on end. The work consumed months. Engineers barely went home. The laboratory operated around the clock, 3 shifts cycling through the same grinding routine: melt, cast, roll, heat treat, age, test, record, repeat. Failure became routine. Alloys that showed early promise would crack during rolling, the metal splitting like dry wood. Others aged too quickly, growing brittle instead of strong. Some reacted poorly to the heat treatments, warping or developing internal stresses that made them impossible to machine. The fundamental chemistry of what happened inside an aging aluminium alloy remained mysterious. This was 1917, before X-ray crystallography, before electron microscopy, before materials science existed as a discipline. The engineers worked almost blind, guided only by empirical results and educated intuition about how metals behaved. By spring, they had something. Not a perfect duplicate of German duralumin, the exact German formula remained unknown, but an American answer. The alloy contained approximately 4% copper, 0.5% each of magnesium and manganese, with the balance pure Alcoa aluminium. It could be cast into ingots, rolled into sheets, and machined into complex shapes. After solution heat treatment at 920 degrees Fahrenheit, followed by quenching in cold water, then natural aging at room temperature for 4 days, the alloy developed a tensile strength exceeding 55,000 pounds per square inch, nearly 4 times stronger than pure aluminum, approaching the strength of mild steel at a third the weight. It could be riveted, welded, formed into spars and ribs and longerons, all the structural members an aircraft required. And crucially, it could be manufactured at scale, using equipment and processes Alcoa already possessed. They designated it 17S, Alloy 17, in the S series of precipitation hardening aluminum alloys. The name was prosaic, almost deliberately uninspiring, the kind of engineering designation that revealed nothing about the metallurgical breakthrough it represented. But men who understood metals recognized what had been achieved. For the first time, America possessed a domestically produced aluminum alloy suitable for aircraft construction. The country would not have to beg Britain and France for metal. American factories could build American aircraft with American materials. The aviation industry, such as it existed in 1917, suddenly had a foundation upon which to build. The War Department's response was both immediate and overwhelming. By June 1917, as American troops began arriving in France to find themselves ridiculed by French and British veterans who called them doughboys and doubted their fighting capability, military procurement officers descended upon Alcoa with contracts for thousands of tons of 17S. The scale shocked even Alcoa's executives, who had grown accustomed to large orders, but nothing of this magnitude. The military wanted aluminum not just for aircraft, but for every conceivable application: engine components, ammunition boxes, mess kits, canteens. 17S, designed specifically for aircraft, found itself diverted to dozens of uses. Alcoa's smelters, rolling mills, and fabrication plants shifted into wartime production mode, running 24 hours a day. The company built new facilities. It recruited metallurgists from universities. It trained workers who had never seen aluminium processed. In 18 months, Alcoa's output of aircraft-grade aluminium alloy increased from essentially zero to over £60 million annually. But making the metal was only half the battle. Aircraft manufacturers, Curtiss, Boeing, Martin, Thomas Morse, a dozen smaller firms, had built their businesses around wood. Their engineers understood spruce, ash, linen fabric, and dope, the clear lacquer that waterproofed and tightened the fabric stretched over wooden frames. Metal was foreign, almost alien. It required different tools, different techniques, different thinking. Wood could be carved, shaped with draw knives and spoke shaves, joined with glue and screws. Metal demanded precision machine work: shears to cut sheet stock, brakes to form flanges, drill presses to punch rivet holes in exact patterns, hydraulic presses to stamp complex shapes. Riveting alone, the method of joining metal sheets that would define aircraft construction for the next 70 years, required skills American workers did not possess. The aviation industry effectively had to be rebuilt from scratch, transformed from a craft-based enterprise of master carpenters into a modern manufacturing system capable of producing metal aircraft in quantities measured not in dozens, but in thousands. The military's solution was characteristically American in its scope and audacity. In the summer of 1917, the War Department established the largest single industrial contract in American history to that date, a $1 billion appropriation, $1,019,17, equivalent to roughly $25 billion today, for military aviation. The government would build entire factories, train entire workforces, create from nothing an aviation industry capable of supplying not just American forces, but Allied forces across Europe. The contract specified production targets that seemed fantastical: 22,000 aircraft and 44,000 engines to be delivered by mid-1918. It was impossible. Everyone knew it was impossible. but the order stood. America had spent 3 years watching European nations bleed themselves white in trenches, and the national mood demanded action, results, proof that American industrial might could succeed where European armies had failed. The reality was predictably more complex. Aircraft production in 1917 could not simply be scaled up like automobile manufacturing. Each plane was still largely handmade, components fitted and adjusted by skilled workers, who spent days assembling what should have been standardized parts. Engines were worse. The Liberty engines American factories produced suffered from quality control problems so severe that pilots joked they were more dangerous than German gunfire. But 17S at least performed as promised. The alloy could be worked, shaped, and formed by workers with only weeks of training. It did not require the intuitive understanding of wood grain that had made aircraft carpentry almost an art form. Specifications could be written, drawings drafted, tolerances defined. A rivet hole drilled in Pittsburgh would align with a rivet hole drilled in Buffalo because both were measured from the same datum points on blueprints drawn to the same standards. By late 1918, American factories had produced approximately 11,000 aircraft, half the ambitious target, but still an unprecedented industrial achievement. The majority were training aircraft, biplanes that taught pilots basic flight skills. But hundreds were combat types, DH-4 observation planes, copies of a British design but built with American engines and American aluminum, SE-5 fighters, Curtiss JN-4 Jennies that would train a generation of post-war civilian pilots. Nearly all incorporated 17S components. The alloy formed engine mounts that absorbed vibration. It became cowlings that streamlined fuselages. It reinforced wing spars at points of maximum stress. In some designs, 17S made up 40% of the aircraft's structural weight, replacing not just wood but steel, which was heavier, and brass, which was scarcer. The American Expeditionary Forces arrived in France with an air service that grew from a joke into a formidable force. By the armistice in November 1918, the American Air Service operated over 740 aircraft at the front, organized into 45 squadrons. They were not the largest air force. Britain and France each fielded several times that number, but they were competent, well-equipped, and, crucially, no longer dependent on European suppliers for basic materials. American pilots like Eddie Rickenbacker, who would become the war's top American ace with 26 confirmed kills, flew aircraft whose aluminum came from Pittsburgh, whose alloy had been invented in laboratories within sight of the Allegheny River. But the true impact of 17S emerged not during the war, but after it. The armistice in November 1918 ended military production almost overnight. Factories geared for wartime output found themselves with cancelled contracts and warehouses full of unsold inventory. The aviation industry, which had barely existed in 1917 and had swollen to employ nearly 200,000 workers by 1918, collapsed. Aircraft manufacturers went bankrupt. Pilots returned from France to find no commercial aviation industry to employ them. The great billion-dollar aviation program appeared, in retrospect, to have been a waste, arriving too late to affect the war's outcome, producing aircraft that were obsolete before they reached the front, squandering resources on an industry that evaporated the moment peace returned. Yet something profound had shifted. The metallurgical knowledge did not disappear. The engineers who had learned to work with 17S did not forget their skills. The industrial infrastructure, the rolling mills, the heat treatment furnaces, the testing facilities, remained. And most importantly, 17S had demonstrated that aluminium alloys could be manufactured at scale, consistently, with properties that could be specified and relied upon. This was not a trivial achievement. In 1917, aluminium had been promising but unreliable, suitable for experimental aircraft but not for serious military or commercial aviation. By 1920, aluminium was simply the material aircraft were made from, as fundamental to flight as engines and propellers. The 1920s saw the gradual birth of commercial aviation, and 17S was there at the beginning. The Ford Trimotor, that corrugated metal beast that became the first widely successful commercial airliner in America, used 17S in its wing spars and fuselage structure. Charles Lindbergh's Spirit of St. Louis, the Ryan NYP monoplane that crossed the Atlantic solo in 1927 and captured the world's imagination, incorporated 17S components. Military aircraft that would define the interwar period, the Boeing P-12 fighter, the Martin B-10 bomber, the Curtiss Hawk series, all relied on aluminium alloys descended directly from the wartime metallurgy that produced 17S. And the alloy continued to evolve. Alcoa's metallurgists, no longer working under wartime pressure, revisited 17S with more sophisticated understanding. They experimented with composition tweaks, heat treatment modifications, aging schedules. They developed 17ST, a variant that was heat-treated by the manufacturer rather than by the fabricator, delivering more consistent properties. They created 24S, which added more magnesium and became the standard aircraft alloy of the 1930s. They pioneered 2024, which would become one of the most widely used aluminum alloys in history, still in production today, still flying in aircraft built in the 21st century. Each generation learned from the previous one, but the lineage traced back to that winter laboratory in Pittsburgh, where engineers raced against time and ignorance to create an alloy that did not exist. The Second World War would vindicate everything. When Nazi Germany launched its invasion of Poland in September 1939, the Luftwaffe flew aircraft built almost entirely of aluminium, advanced, modern, terrifyingly effective machines that swept Polish, French, and British aircraft from the skies with contemptuous ease. But by then, America had spent 2 decades developing not just aluminium alloys, but the entire industrial system required to produce them in wartime quantities. When the United States entered World War II in December 1941, Alcoa and its competitors could supply aluminium in volumes that would have seemed impossible in 1917. American aluminium production in 1943 alone exceeded total world production from all sources in the entire decade of the 1930s. That aluminium became B-17 flying fortresses, each one containing over 17,000 pounds of aluminium alloy. It became P-51 Mustangs, the long-range fighters that escorted bombers to Berlin and back. It became C-47 transports that dropped paratroopers over Normandy and supplied forces across the Pacific. It became the 300,000 aircraft American factories produced during the war, an output so staggering that it represented 2/3 of all aircraft built by all combatants worldwide. German engineers, ironically, had failed to maintain their early advantage. They had pioneered duralumin, had built the knowledge and infrastructure first, had equipped their aircraft industry with the tools and techniques for metal construction years before America did. But Nazi Germany's war economy, despite its reputation for efficiency, suffered from chaotic planning, competing bureaucracies, and a fatal tendency to prioritize ideological purity over industrial rationality. German aluminium production never matched demand. Luftwaffe fighters in 1944 incorporated wood components to save metal. Desperate shortages forced designers to use steel where aluminium would have been superior, adding weight and reducing performance. The HE-162 Volksjäger, a late-war jet fighter, used wood in its fuselage because aluminum simply was not available. Germany had invented the aluminum age of aviation, and then lost it to a nation they had assumed could never catch up. Japanese engineers faced similar constraints. Japan's aluminum industry, dependent on imported bauxite and limited electrical power, could never produce the quantities required for the kind of total air war the Pacific Theater demanded. Japanese aircraft, superbly designed and initially superior to their American counterparts, grew increasingly obsolete not because Japanese engineers lacked skill, but because they lacked material. By 1945, Japan was building kamikaze aircraft from wood and fabric, one-way suicide machines that represented not just military desperation, but industrial collapse. American aluminium, by contrast, flowed like water. Alcoa's original monopoly had been broken by wartime antitrust action, but the effect was to increase total production rather than limit it. Reynolds Metals, Kaiser Aluminum, a dozen smaller producers all contributed. The Pacific Northwest's vast hydroelectric resources, dams built during the Depression as public works projects, provided the enormous quantities of cheap electricity aluminum smelting required. Bauxite mines in Arkansas and Jamaica supplied raw material. The entire system operated at a scale unimaginable in 1917, and it all traced back to the wartime crash program that produced 17S. The men who created that alloy did not live to see its full impact. Most were anonymous, engineers and metallurgists whose names appeared only in patent filings and technical papers read by specialists. They received no medals, no public recognition. When victory came in 1945, the public celebrated pilots and soldiers, generals and admirals, the men who fought rather than the men who made fighting possible. This was as it should be, perhaps. But the metallurgists understood what they had contributed. They had taken a metal that was soft and made it strong. They had taken an industry that did not exist and given it the materials to build upon. They had solved a problem that, unsolved, might have cost America the ability to wage modern war. There is a monument of sorts, though few recognize it as such. Every commercial airliner that departs from every airport in the world contains aluminum alloys descended from 17S. The Boeing 747, that magnificent creature that democratized air travel and shrank the planet, carries 147,000 pounds of aluminum in its structure. Wings, fuselage, tail, all of it alloy families related to what Alcoa created in 1917. The Airbus A380, the largest passenger aircraft ever built, uses advanced aluminum-lithium alloys. But the metallurgical principles remain those discovered and refined during the first half of the 20th century. Military aircraft, commercial transports, private planes, helicopters, even spacecraft. The Apollo lunar modules were aluminum. The Space Shuttle's external structure was aluminum. The International Space Station's modules are aluminum. Humanity's conquest of the sky, from the first military scouts over France to the rovers we have landed on Mars, rests upon the metallurgy that began in earnest during those desperate months of 1917 when America needed aluminium for aircraft and had none. The story of 17S is not a story of individual genius, though brilliant individuals contributed. It is not a story of American exceptionalism, though American industrial capacity proved decisive. It is, instead, a story about the intersection of necessity and capability, about what happens when a nation suddenly discovers it lacks something essential and decides, collectively, urgently, without full understanding of whether success is even possible, to create what it needs from nothing. The engineers in that Pittsburgh laboratory did not know if they would succeed. They could not know. The science was too new, the timeline too short, the stakes too high. But they tried, systematically and relentlessly, and they succeeded not because success was inevitable, but because failure was unacceptable. There is something profoundly American in that, in the stubborn refusal to accept that a problem might be unsolvable simply because no one has solved it yet. European nations, possessed of longer histories and deeper cultural memories, understood the limits of what could be achieved quickly. They knew that metallurgical breakthroughs took years, that industrial systems required decades to mature, that wars were won by whoever had prepared better beforehand. And they were right, mostly. But America in 1917 did not have years or decades. It had months, and so it attempted the impossible and made it routine. When German officers interrogated American pilots captured during World War II, and this happened thousands of times across Europe, they often asked about American industrial capacity. How many aircraft could America build? What were production rates? How did American factories achieve such volume? The pilots rarely knew specifics, but they understood the essential truth. American industry had no practical limits. If war required 300,000 aircraft, America would build 300,000 aircraft. If bombers needed to be larger, carry more bombs farther, America would build larger bombers. The material constraints that throttled German and Japanese production simply did not apply. American factories had access to functionally unlimited aluminum, steel, copper, rubber, oil, all the basic materials modern war consumed in quantities that would have seemed insane in any previous conflict. That abundance had not existed automatically. It was created, built deliberately through decades of industrial development, infrastructure investment, and metallurgical innovation that began, in aviation's case, with desperate men in a cold laboratory trying to duplicate an enemy alloy they had never seen. They succeeded, and because they succeeded, a generation later, America could build the aircraft that filled the skies over Europe and the Pacific, that broke the Luftwaffe, that isolated Japan, that made Allied victory possible. The aluminium flows still. Alcoa's descendant companies still produce aircraft alloys. The processes have been refined, the compositions optimized, the testing grown more sophisticated. Modern aluminium-lithium alloys achieve strength-to-weight ratios those 1917 engineers would have considered impossible. Aluminum-scandium alloys, aluminum matrix composites, advanced heat treatments. The metallurgy has progressed far beyond 17S. But every improvement builds upon what came before, and what came before began in earnest during those months when America discovered it could not build aircraft because it lacked the metal, and decided to invent the metal it needed. There are no statues, no memorials. The men who created 17S are forgotten outside of specialized metallurgy textbooks. But their legacy endures in every aircraft that flies, in the entire global infrastructure of commercial aviation that connects continents and makes the modern world possible. They gave America, and through America the world, the material foundation for powered flight at scale. They took aluminum, that soft, silvery metal that had been a curiosity and a commodity, and made it structural, reliable, essential. They did it quickly, under pressure, without full understanding of what they were creating, and they succeeded. That success, quiet and technical and utterly unglamorous, changed history as surely as any battle or treaty. Because when nations possess the ability to build what they need when they need it, when industrial capacity can be mobilized and directed toward problems that seem insoluble, when engineers can take an enemy's invention and improve upon it within months, when all of that is possible, the calculus of power shifts. Wars become contests not just of courage or strategy, but of industrial depth, of who can build more and build it faster. And in that contest, America had discovered, almost by accident, that it possessed advantages no other nation could match. The aluminum came from American ore, smelted with American electricity, shaped by American workers in American factories, installed in American aircraft flown by American pilots. But it began with knowledge, stolen knowledge, borrowed knowledge, reverse-engineered knowledge, and finally American knowledge, created through grinding systematic experimentation when no other path existed. That knowledge, once created, could not be unmade. It existed, permanent and transferable, ready to be applied whenever needed. And in the years to come, it would be needed, again and again, as the promises and dangers of powered flight shaped the 20th century in ways those 1917 engineers could never have imagined. They worked through that winter and into spring, testing alloys in a cold laboratory in Pittsburgh, while Europe tore itself apart. They did not expect glory. They expected results. And they delivered results that made the sky accessible, that made aviation practical, that made the modern world possible. This is their monument. Every aircraft, every flight, every time someone crosses an ocean in hours rather than days. The metal remembers, even if we have forgotten.